in the overall scheme of things, well, fossil fuels are the dominant energy source, but we want to move away from them because of multiple reasons, both global warming and the fact that they are non-renewable, right? So we need to have some sort of a fuel source which we can continue to use for hundreds, thousands of years, okay? And biofuel is one option, which we have already discussed briefly. Another option is hydrogen, basically, right? And or hydrogen and hydrogen associated fuels, or like ammonia and ethanol, methanol, and all of these e-fuels that again can be created, synthetic fuels that can be created from hydrogen. Now, when we talk about hydrogen globally, uh, the way the hydrogen is produced is mainly through reforming, right? Reforming of fuel. It can be methane reforming and SMR process, can be oil reforming, which accounts for 29%. Uh, or it could be gasification or water electrolysis. But when you look at gasification and water electrolysis, put together, they contribute less than 21% of the global hydrogen production, right? So it's mainly happening through steam methane reforming, 49%, and about 30% happening from oil reforming. So when we look at it, well, of course, steam methane reforming is a better way of doing it than oil reforming. It's cheaper as well, and so we'll focus mainly on steam methane reforming, and the process remains the same. So we'll discuss steam methane reforming, and then we'll talk about some other options available for producing hydrogen apart from steam methane reforming, starting from a fossil fuel, right? And lastly, we will also touch upon water electrolysis to talk about a process which can make use of renewable energy to again create hydrogen. Now, when we talk about steam methane reforming or reforming of natural gas, which is mainly methane, it's a very mature technology. It's used currently in the industry, mainly in refineries, because they need a lot of hydrogen in there, and it's used for producing hydrogen, which is basically called gray hydrogen, as per the color palette associated with different hydrogen production processes, depending on their carbon footprint, right? Or depending on the source of hydrogen, basically. Now, as I said, steam methane reforming or SMR for short is a very mature technology. It's the most dominant pathway, as we see from this pie chart here. And so let's try to understand a little bit on how this works, right? So what you do in steam methane reforming is that we make use of a methane source, typically natural gas, which reacts with high temperature steam, okay, somewhere in the 700 to 1000 Celsius range, under relatively high pressure, 3 to 25 bar, and you need a catalyst when this reaction is going on. And the purpose of this is simply to reform methane to produce hydrogen, right? And what you get is not just hydrogen, because there's carbon in methane, so you get hydrogen, but you also get some amount of carbon monoxide, okay, and very small amount of carbon dioxide. So when we look at the reaction itself, this is the main reaction that's happening. This is methane, which is coming from natural gas. Okay, natural gas is usually 80% methane. So methane from natural gas reacts with steam, right? H2O at I would say, yeah, intermediate temperatures and pressures, and in presence of a catalyst to give us 3 moles of hydrogen plus 1 mole of carbon monoxide. So 1 mole of methane is giving you 3 moles of hydrogen. Okay. Now we don't stop here, of course. For making this reaction happen, the steam methane reforming, we had to provide some energy. It's an endothermic reaction. So we ended up with hydrogen plus CO. So what we need to do is now next, well, we take the CO and then again make it react with steam again in another reaction, which is commonly called as the water gas shift reaction. Water is H2O and gas being the CO there. And in the water gas shift reaction, we produce more hydrogen, and this also happens in presence of a catalyst. So both reactions that we are talking about here, steam methane reforming reactions right here, and the water gas shift reaction, both of these happen in presence of a catalyst, and both happens in presence of steam. So first is methane reacting with steam, and then second is the CO that you produce. It reacts with steam to produce CO2 and some more hydrogen. So in total, for 1 mole of fuel, you get 4 moles of hydrogen. 3 moles from the methane reforming and 1 mole from the water gas shift reaction. So it's a very good way of producing hydrogen, and it's as we discussed, it's the most mature. It's a very mature technology. It's the most dominant way. And although I'm sort of making use of methane here to show how this entire process works, but you can do exactly the same thing with other fuels as well. So you can use ethanol, propane, gasoline, and others. But yeah, natural gas is mainly used, and natural gas, although we said it's mainly methane, but it also contains ethane, right? So C2H6 and propane, C3H8, and others. And so the process is exactly, or it's very similar to what we have defined here. Okay, so this is steam methane reforming. Key point is it's endothermic. It requires a catalyst, right? And it produces some CO2, of course, but this CO2 can be captured. And if you capture the CO2 from steam methane reforming process, then the hydrogen that you obtain is called blue hydrogen. If you do not do carbon capture, then it's called gray hydrogen. Okay. Now, moving on, steam methane reforming, although it's a very mature technology, it's the most dominant way of producing hydrogen. It is not the only way, right? Of course, we want to come up with other ways which reduce the energy requirement, make it cheaper to produce hydrogen. So, the two other, let's say, options that are being explored on a research basis globally are basically partial oxidation and autothermal reforming. There are many other options that are being explored currently, but let's limit to these two. When we talk about partial oxidation, it's essentially instead of reacting with steam, what you do is you make the methane or any other hydrocarbons that you have in a natural gas. You make them react with oxygen. So basically, what you're doing is some sort of a combustion reaction, but incomplete combustion. A key difference here is that normally when you talk about combustion, we do combustion in air, right? So air is a mixture of oxygen plus nitrogen. So for every mole of oxygen, you have 3.76 moles of nitrogen in the air, right? But when we talk about partial oxidation, it is just the oxygen that the methane reacts with. So we just supply oxygen to methane, and we supply less oxygen than what's needed, right? Stoichiometric amount basically means the amount you need for complete combustion, but we provide less than that. We provide less oxygen than that's needed for complete combustion, and the idea is simply because we don't want complete combustion to happen. We only want this reaction, which is an exothermic reaction, right? It produces heat. We want this reaction to partially oxidize the hydrocarbons that we have, methane, for example, and it produces mainly hydrogen and carbon monoxide. Now, this carbon monoxide, again, you take it, you make it go undergo the water gas shift reaction. Okay, just like we explained in the previous slide. So carbon monoxide plus steam gives us CO2 plus hydrogen, right? So you get more hydrogen from the next step. But overall, this is another way of producing hydrogen. It produces less hydrogen per unit of fuel because here we get a total of 3 moles of hydrogen for 1 mole of methane as compared to 4 moles of hydrogen in the previous scenario for steam methane reforming. But this is something that does not require a catalyst, right? And it produces, and you don't even have to supply heat. It's not an endothermic reaction. So it's an interesting reaction. The economics still do not favor it, which is why steam methane reforming is the most dominant. So of course there are some issues that need to be resolved and to make it more economic. But this is another promising way of producing hydrogen. Now, the last way that we want to discuss here, that is another promising way, is autothermal reforming. Now, autothermal reforming is sort of a combination of steam methane reforming and partial oxidation. That is, it's a combination of the previous two methods that we described. Now, what happens is that in autothermal reforming, methane is going to react with oxygen in partial oxidation process, which is an exothermic process. So some part of methane reacts with oxygen and produces hydrogen and CO, and the remaining part of methane reacts with steam, right, which is an endothermic process. So what you have here is one reaction of methane producing heat, another reaction of methane consuming heat. So what we have is a reaction which is thermally neutral, right, or a reaction where you don't need any external source, nor do you have to reject heat. So this is uh, almost like a constant temperature process, and it uh, it produces less hydrogen, slightly less hydrogen as compared to steam methane reforming, but it produces more hydrogen as compared to partial oxidation. It's sort of a hybrid process, right, between partial hybrid of partial oxidation and steam methane reforming. The advantage being that, yeah, you don't need an external source, and you're increasing the amount of hydrogen produced as compared to partial oxidation. Okay, so in terms of uh, the hydrogen production, right? So steam methane reforming produces the most amount of hydrogen per unit of fuel. Next is autothermal reforming, and last is partial oxidation. Okay. The advantage with partial oxidation, you don't need a catalyst. It's an exothermic process, so you don't need any energy supply. You don't need any heat supply. Okay. Autothermal is a compromise, and steam methane reforming well requires catalyst, requires also the external energy source. Okay. So now the only challenge that makes these partial oxidation and autothermal reforming (ATR) less economically favorable is that they rely on partial oxidation, right? And partial oxidation needs pure oxygen. Okay. So if you need pure oxygen, it means that you need to employ air separation units, ASU as they are commonly called, to take in air, which is a mixture of oxygen and nitrogen, as we discussed, and separate oxygen from it, and this oxygen then goes into the oxidation process. So this air separation units would sort of separate oxygen and nitrogen primarily by cooling them down to below their boiling point. So it's an energy intensive process that requires a lot of energy, right? So yes, we are saving energy in terms of not providing the thermal energy needed for making the process happen like we need for steam methane reforming, but well, we need air separation unit, which is another energy sink. So overall, steam methane reforming is the process which has the highest thermal efficiency and the highest is the most dominant method, but these two are promising and they're still under current research. Okay. Now, lastly, if you want to produce methane not from a fossil fuel but from renewable energy completely, then we can make use of water electrolysis to make it happen. Now, water electrolysis simply is an electrolyzer which takes an incoming water stream and it splits that into hydrogen and oxygen. Okay, you can then still sell this oxygen as well, right? On top of the hydrogen that you get from here. Now, electrolysis process, of course, makes use of a lot of electrical energy for making it happen, and it's in principle it's just a reverse process of what happens in a fuel cell, right? In a fuel cell, you provide hydrogen, takes the oxygen from the air, and then it produces electricity. Here, it's the opposite. Fuel cell produces electricity and also some amount of water, right? So here is the opposite. You provide water, and the input is water, and the output is hydrogen. Okay, it's an interesting process. The electrical energy that you need for water electrolysis can come from renewables, which will make it some having less carbon footprint than the other options. But it's pretty costly for now, right? If you want to look at the numbers involved, if you uh, for doing electrolysis versus steam methane reforming for hydrogen production, you can look through this G hydrogen calculator. For using the combined cycle power plant that's and used in Korea. So this model is available in the list. So you can just click that link, select this model, do a combined cycle power plant, maybe do 2-in-1 configuration, two gas turbines for one steam turbine, and then see for yourself how much amount of water is needed and how much amount of electrical energy is needed for producing the hydrogen using water electrolysis versus how much amount of methane and how much amount of water again is needed for producing hydrogen using steam methane reforming, right? So it's something interesting to look at. Okay, well, that will end the class. We'll continue with the numerical problems in the class tomorrow.